Next, we want to finish off our unit on magnetism by looking at the interaction between two wires with current going through them. So now we've looked at how two permanent magnets interact with each other, how they interact with a magnetic field, and we've looked at how a wire interacts with a permanent magnet. So now we want to look at the interaction between two wires. So in this case, we have two wires that have a current that is flowing into the page. So let's think about the force on wire 2 here on the right. So the magnetic field generated by wire 1 will cause a force on wire 2 that is based on the current and length of the wire. So we know that the force on wire 2 will be the magnetic field times the current times the length times the sine of the angle theta between the magnetic field and the current. So we know the current and the length, so that's good, but we also need to find the magnetic field generated by wire 1. So a straight wire generates a magnetic field that is mu naught times the current of 1 divided by 2 pi r, where r here is going to be the distance between the wires. So the critical question here, though, is what is the direction that the force faces? Well, the current of 1 is going into the page, so we're going to use our first version of the right-hand rule. So we're going to find that the pointer finger is going into the page, and the magnetic field generated by 1, so there we use the second version of our right-hand rule, and that's going to tell us that the magnetic field is pointing down the page. So that means our index finger goes into the page, our middle finger points down, so the force on wire 2 is going to push to the left. So that means that since they are at 90 degrees angle, that means that the force on our wire 2 will be the current of 2 times the length of 2 times the magnetic field of 1, which is mu naught times the current of 1 divided by 2 pi r, and where again r is the distance between the wires. Alright, so if we are a bit lazy, we can just use Newton's third law to say that the force on 1 needs to be the same magnitude but the opposite direction to the right. If we want to do a sanity check, the magnetic field generated by wire 2 will point up at wire 1, right? So our thumb points into the page, so to its left our fingers will point up, and so that means our index finger points into the page, middle finger is pointing up, and so now the thumb is pointing to the right. So the directions here check out. So for magnitude, the distance is the same, and I guess current 1, current 2 will switch places, I suppose, but it's really the same thing. So this gives us a rule about the force between two moving currents. So remember, magnetic forces are about the interaction between two moving charges. So the two currents times a constant divided by the area of the shape that projects out of that surface. So it's a little bit like a funhouse mirror version of Coulomb's law, but it should make sense that as the current increase, the forces will increase, and that as the distance decreases, then the force will increase. So one important example is when a loop of current is put inside of a uniform magnetic field. In this case, the field puts a torque on the current loop and will try to make it spin. So if we look at point A here, the current is pointing up, the magnetic field is pointing to the right, so the force is pointing into the page. At C, the current and the field are aligned with each other, so well, guess what the force is? So yeah, it's 0, right? Since the current and the magnetic field are aligned, so well, there's no force. If we look at D now, the current is pointing down, the magnetic field is still to the right, but now the force is pointing out of the page. So the left side will be pushed into the page, and the right side will be pushed out of the page. So that means that the loop will kind of want to spin here. One important example of how these kinds of magnetic fields and electric fields interact is a velocity selector. So if you accelerate a charged particle into the chamber we have here, where a magnetic field is pointing into the page and the electric field is pointing down, what happens? Well, the electric field is simple enough. The force is pointing down, so and the force will be Q at E, the charge times the electric field, and I guess I'm assuming here the charge will be positive. For the magnetic force, so our positive particle is moving to the right, and the magnetic field is into the page, so the force will point up. So if we draw a free body diagram, the electric force will point down and the magnetic force will point up. So a particle that experiences no net force will then have a electric force and a magnetic force that are equal to each other. If those forces aren't equal, then it's going to crash into the sides of our chamber, so those particles are all going to disappear. So for the forces to be equal, QE, our electric force, must be equal to QVB, the magnetic force. And since sine theta here, theta is 90 degrees, so yeah, it's just QVB. So the charges will cancel out also, so that means E, the electric field, is equal to the velocity times the magnetic field, and the velocity is equal to E divided by the magnetic field. So only charged particles with a specific velocity will travel across this chamber. All other particles will be deflected into the walls. So if we scan through, say, different electric field strengths and then count the ions that make it through the chamber, we can identify the sort of population of the velocities of particles that are traveling into our chamber. In a mass spectrometer, you would accelerate your particles through a certain electric field, so you would then know the kinetic energy and the velocity, so you could then solve for the mass-to-charge ratio. That means you could identify the fragments of a molecule very quickly. Okay, so I think that wraps up our unit on magnetism. So next week we're going to look at inducing electric currents. That's maybe the trickiest unit in the course, so look forward to that. Also, I guess you guys have some questions to do here on the classwork assignment, so we have those to do for Friday, and you'll have a homework assignment due on Monday morning, so don't forget about that either. All right, good luck and take care of yourselves.